This is one of my favorite little elegant things. Suppose we're looking for the length of this arc, so we have some function we have expressed in parametric equations, and we're looking for the length of this as t goes from 1 to 2. And who knows about this? You know, it's not exactly a part of a circle, so we're going to have a hard time figuring out the length. But as we know with calculus, what we can always do is break this into teeny, teeny, tiny pieces. And we still have that idea of local linearity. So let's assume that both x and y are differentiable functions. So in fact, the curve that we get is also differentiable, so that I do have local linearity at my disposal. So if I was just going to take a little piece of this, and I'm just going to change color, I'm just going to take a little piece of this, and I'm going to wonder what the length of that is. But since I can assume it's locally linear, well, I can break this up into a little bitty right triangle, in which case the horizontal part I can call, well, I don't know, that's delta x, and this is delta y, and let's call this L, just for the sake of it, L. So if we could add up all of these pieces, wouldn't we be okay? So I could say that this L here, so just this one little piece, well, I know that I could use the Pythagorean theorem. So here's what I'm going to say. This delta x is between, well, two different x values. So I'm going to say, in fact, I'll say this, delta x is going to be x of, let's say, t sub I minus x of t sub I minus 1. And I could do the same thing with y. So then L is going to be the square root of this, kind of complicated, x of t sub I minus x of t sub I minus 1. That whole thing squared plus the same thing with y, right? I'm going to do the same thing. Y of t sub I minus y of t sub I minus 1 squared, right? So just the Pythagorean theorem. However, this is calculus, so what we can call into play is this mean value theorem. So x, in fact, is a differentiable function. And by the mean value theorem, I know that if x is a differentiable function, then over some interval, let's say where t goes from t sub I to t sub I minus 1, here's what I can say, that there's going to exist some t star, let's say, such that x prime of t star is going to be equal to x of t sub I minus x of t sub I minus 1 all over t sub I minus t sub I minus 1. And here's what I'm going to do. I'm going to call this denominator, I'm just going to call that delta t. So what I'm saying is that my x of t sub I minus x of t sub I minus 1 can be replaced by x prime of this t value times delta t. So as delta t goes to infinity, I can replace this part, I'm going to go back, this part of my little Pythagorean theorem equation with x prime of t delta t. And in fact, since y is also a differentiable function, I can do the same thing. So here's what my Pythagorean theorem is going to look like eventually. I'm going to say that each of the hypotenuses is going to be equal to the square root of x prime of t delta t squared plus y prime of t, whoops, sorry, didn't mean to do that, y prime of t delta t squared. And you know that what we're going to do is take this Riemann sum, add all of these together as delta t approaches infinity. So eventually we're going to end up with something like this. We're going to end up with the antiderivative of this thing. And what I'm going to do is I'm going to write this out a little bit. So we're going to have the antiderivative of, we're going to have x prime of t squared. We're going to have delta t squared. Delta t squared plus, write that, y prime of t squared delta t squared. And I'm just going to factor out these delta t squares. And in fact, if I factor them out of each of these terms, then I can take the whole delta t squared out of the radicand. So eventually we're just going to end up with the total arc length is going to be the antiderivative of the square root of x prime of t squared plus y prime of t squared dt. And we just have to keep in account of what our t values are. That gives us this curve.